Welcome to Lesson 3, Simple Machines. In this lesson we will cover what machines do, the types of simple machines, and the advantages they offer us in accomplishing work. A definition we will use for a machine is that it is any device with which work may be accomplished. Machines are used to perform a variety of functions. One of those functions is to transform energy. An example of this is when a coal-fired power plant transforms the energy in coal into electrical energy. They're also used to transfer energy. An example of that is when the connecting rods in the engine transfer the energy from the cylinder heads to the crankshaft. They're also used to multiply force. An example of that is when we use our levers to multiply the force we apply to one end to lift a greater weight on the other end. They're also used to multiply speed, for example when we ride a bicycle, where we can increase our speed without increasing our effort or force. They're also used to change the direction of force. One example of that is when we raise a flag on a flagpole. As we are pulling down on the rope on the flagpole, the flag is moving in the opposite direction, upwards. There are 6 basic types of simple machines: a lever, a gear, a pulley, an inclined plane, a wheel and axle, and a screw. The first of the simple machines we will discuss is the lever. Levers are typically used to multiply a force, but are sometimes also used to multiply a distance. There are 3 basic parts in all levers. First is the fulcrum, or the pivot point. The second is the point where the force or effort is being applied. And the third is the point where the resistance or weight is being moved or lifted. There are 3 classes of levers. In the first class, the fulcrum lies in between the force and the weight. In the second class, the weight lies in between the force and the fulcrum. And in the third class, the force lies in between the weight and the fulcrum. There are 4 variables used in solving our lever problems. If we know the values for any 3 of them, we can use that information to find the 4th by using the equation capital L over little l equals W over F, where capital L is the length from the fulcrum to the point where force is applied, little l is the length from the fulcrum to the point where the weight is being moved, F is the force, and W is the weight. Here we have an example of how to solve for the unknown variable in a first-class lever we are using to lift a 100-pound weight. We are given a distance from the weight to the fulcrum of 1/2 a foot and a distance from the point where the force is being applied to the fulcrum of 3 1/2 feet. When we insert the given values into the formula, we get 3 1/2 feet divided by 1/2 foot equals 100 pounds divided by F. Once we solve for F, we find that using this lever, we need 14.28 pounds of force to lift the 100 pounds of weight. In this example of a second-class lever, we are given a distance from the fulcrum to the point where the weight rests of 12 inches and a distance from the fulcrum to the point where the force is being applied of 48 inches. We will use our lever equation to solve the amount of force required to lift the 200 pounds. We will begin by inserting our known values into the lever equation, and once done, we get 48 inches divided by 12 inches equals 200 pounds divided by the force being applied. Solving for F, we find that we need 50 pounds of force to lift 200 pounds with this lever. Third-class levers are often used to move a weight through a greater distance than a force is being applied, rather than to multiply the force to lift a greater weight. Actually, it takes more force to lift a weight with a third-class lever. The advantage gained is one of distance or speed. In this example, we will try to determine how much force is required to lift 200 pounds 4 feet when we are only applying that force through a 1/2 foot. Again, taking our given values and plugging them into our lever formula, we get 1/2 foot divided by 4 feet equals 200 pounds divided by the force. Solving for F, we find that we would need 1,600 pounds of force to lift 200 pounds with this lever. When describing the mechanical advantage given by a simple machine, it is the increase in force or speed or distance produced by a mechanical device. We can determine the mechanical advantage of a lever by either dividing the weight by the force being applied, or by dividing the length from the fulcrum to the point where the force is applied by the length from the fulcrum to the point where the weight is being moved. The equation for finding the missing values involving an inclined plane are similar to the equation for levers. It is capital L over little l equals W over F, where capital L is the length of the ramp measured along the slope, little l is the height of the ramp, F is again the force, and W is again the weight. In this example of an inclined plane problem, we are given a weight of 500 pounds that needs to be lifted up the ramp. We are given a length of the ramp of 12 feet and a height of the ramp of 4 feet. When we plug these given values into our equation, we get 12 feet divided by 4 feet equals 500 pounds divided by our force or our effort. Once we solve for our force or effort, we find out that given this inclined plane and the weight needed to be lifted, we would need 166.7 pounds of force to lift 500 pounds up this ramp. Pulleys are simple machines that allow us to move a greater weight than the force being applied and or to change the direction of force. Here I see that without a pulley, if I wanted to lift 100 pounds upward with a 100-pound rope through 100 feet, I would have to apply 100 pounds of force upward for 100 feet. By using the pulley as depicted here, I can lift that 100 pounds upward 100 feet by again applying 100 pounds of force through a distance of 100 feet. The difference being by use of the pulley in this instance, I have changed the direction by which I need to apply that force. By using two pulleys as shown here, I can lift 100 pounds by applying only 50 pounds of force. But to lift that 100 pounds 100 feet, I would have to apply that 50 pounds of force over a distance of 200 feet. When using 4 pulleys as shown here, I need only apply 25 pounds of force to lift 100 pounds. But if I want to lift that 100 pounds 100 feet, I need to apply that 25 pounds of force to a distance of 400 feet. To determine the mechanical advantage of a set of pulleys, simply count the sections of rope to which a downward force is not being applied. On the picture here to the left, the arrow crosses 2 sections of rope. However, a downward force is applied to one, therefore the mechanical advantage is 1. In the middle picture, the arrow here crosses 2 sections of rope where neither have a downward force applied, therefore the mechanical advantage is 2. In the picture to the right, the arrow crosses 4 sections of rope, none of which have a downward force applied, therefore the mechanical advantage is 4. Gears are used more than any other simple machine. There are many types of gears used in aviation: spur gears, beveled gears, worm gears, and planetary gears. Gears are used to gain mechanical advantage or to change direction. Spur gears have their teeth cut straight across their circumference. Beveled gears are used when a drive shaft and a driven shaft are not parallel to each other. Worm gears are used when an extreme amount of mechanical advantage is needed. Planetary gears are used to reduce the propeller shaft speed. This allows the engine to turn at a higher RPM.